So hello everyone, this is lecture 55 for the mathematical physics. The last lecture we were discussing about the gradient, and we have seen some properties of gradient, and we use this gradient to find the maxima and minima or the saddle point for a function fx, fxy. Okay, so I told you how to find, and I told you about the h value, and by using the h value you can see that if at that point if it is maxima, minima or saddle point. Okay, and how to find those points. So you need to put these fx and fy equal to 0 and then check for the h value. That's how you get your maximum, minimum and saddle point. So we have discussed this example also. So today we will discuss about a directional derivative, means some other applications of gradient. So let's see what is directional derivative. So basically if you have a function f, then in any particular direction how your f is changing, okay, that is called a directional derivative. So let's see how can we define this. The directional derivative for a function f, which is a function of xyz at a point p in the direction of a vector n cap, is defined by, means at any point p in this n cap direction how this f is changing is called a directional derivative. So we can define it this form, means we can, if this is your s distance, then this minus this will give you this divided by this s, means that is how your function is changing in this direction. So this is your directional derivative. So this is equal to df by ds. So how df is changing with ds. So limit s is very small distance. So we'll say that s is tending to 0. Then fq minus fp divided by s is called the directional derivative. So remember the basic definition that how your function is changing in this direction is called a directional derivative. And we have taken this very small distance so that we can check this in this direction. Okay. So your function can be in any direction. So but you find the change in function in particular direction, that is called the directional derivative. Q is a variable point on the line L. So Q can be anywhere. So we will take it a very small distance. So it will be somewhere here on the line L in the direction of n cap, and S is the distance between points P and Q. So if S is greater than 0, then we will say that Q is lying in the direction of n cap, and if S is less than 0, then we will say that Q is lying in the negative direction of P or the n cap, and if P s equal to 0, then we will say that Q is lying on the point P. So that's how we define the line, because in line that's how the things go in a single unit direction. So remember these points. Now let's see how to find the directional derivative. Okay, we know this, but we don't have a single formula in terms of gradient we will find. So let's see. So if you have any line, so how can you find the equation of a line? See first, this whole line or the coordinates on any point is depending on the xyz coordinates, and xyz coordinates are depending on this s. Okay, so first we can write this in this form. Line L is given by r, so which is depending on s, and it can be written in this form: x cap, y cap, z cap. So this is the equation of line where this x is also a function of s, y is also a function of s, and z is also a function of s. So why this is coming thing? Because our function f is function of xyz and xyz are function of s. Okay, so that's why we are getting this thing, because r is something x cap, y cap, z cap, but now because of this r is become the function of s, and x is also function of s, y is also, and z is also. Okay, so so for any line you know how to give a equation of a line. So r equal to, if you have 2 points or any point in the direction, so see, you will take this, if this is your a naught, then a naught plus s n cap will give you what? This will give you your line equation, because from the elementary classes you can remember the how to find equation of line. You must have a point on the line, and you should have the direction of that line. So that's how you can determine the equation of line. So it will be p naught, means the coordinates of this point, plus s multiply n cap. So this will denote this length. So for any point q, you can determine its coordinate by p naught plus s n cap. Okay, so that's how we can write this r equal to p naught plus s n cap. Now let's see how this r is changing with respect to s. So in this line, if you find this r dash, it will be given by x dash, y dash, and z dash. Okay, and this is with respect to s. So dr, r is changing with s as r dash, x is s, x dash, y dash, and z dash. So these are the derivative with respect to s, how r, x, y, and z are changing with respect to s. Okay, so see, if you find the derivative of this, again you have to derive this also with respect to s. This will give you 0 because it's constant, and this is s n cap, so it will be n cap only. So this derivative will be equal to n cap. So what you see here, this derivative of r is nothing but is that direction in which you are finding your derivative, or means your f. Okay, change in f. This is the direction. So now our basic target is to find this directional derivative, that is df by ds, how function is changing with respect to s. So let's see, if this f is function of xyz and xyz are function of s, then we need to write it in form of chain rule. So we can differentiate it. First del f with respect to del x, then with dx with respect to s. So that's how you will write del f by del y, dy by ds, del f by del z, dz by ds. So this will be written in this form because f is function of xyz and xyz are function of s. Now see how this can be written. I mean, this is nothing but x dash, this is y dash, and this is z dash, and this del f by del x, del f by del y, del f by del z are nothing but del x, gradient of f. So this can be written in this form. Now see, you can write this x dash, y dash, z dash in form of vector, and this is also a vector. So this del f is this x cap, y cap, z cap. So we can write del f dot r dash, because this x dash, y dash, z dash is nothing but r dash. So we can write this complete thing in this form, del f dot r dash, because if del f is this and r dash is this, so dot product of this and this will give you this. So that's why this can be written in this form. Now see, this is equal to what? df by ds. So this is nothing but your directional derivative, and where this r dash is nothing but n cap, we already proved this. So directional derivative in any direction at any point is given by this, df by ds equal to del f dot n cap. So remember this formula, very important formula. And now this n cap is nothing but, if you need to find the n cap in the direction of a vector, okay, so you need to find the unit vector in that direction. So that will be a vector divided by a magnitude and del f. So that's how you can write your directional derivative. What is the meaning of this? Means how f is changing in a direction. Okay, so how f is changing in a direction is called the directional derivative at a. Okay, so that's how you can find the directional derivative at a. So let's see the question. Find directional derivative of f. F is given in this form, 2x square plus 3y square plus z square at point p 2 1 3. So this is the coordinate of function, means in the coordinate system. So we need to find directional derivative of f, how f is changing at this point in this direction. So how f, this function, is changing at this point in this direction. So we need to find that. So let's see. So direction is this, so we need to find a unit vector in this direction. So it will be a divided by a magnitude. So it will be under root 1 plus 4, it will be under root 5. So 1 upon root 5 minus 2 upon root 5 here. So this will give you n cap. Now you need to find the gradient of f. So gradient of f will be 4x plus 6y, and this will be 2z. So let's see the gradient of f. So it will be this. Now you need to find the gradient of f at this point 2 1 3, because at this point you need to find this change in the function. So gradient of f at 2 1 3 will be 8x cap plus 6y cap plus 6z cap. Now see, you have this gradient and you have your unit vector, that is a by a magnitude. So you will just substitute the values. So here it will be unit vector, here this vector. So this will give you what? This will give you directional derivative. So it will be minus 1.79. Means in the a direction, this function is decreasing with this rate. Okay, so that's how we find the directional derivative. Now let's see one more thing for the gradient. Gradient as a surface normal vector, let a surface be, means we need to prove that gradient at for any function is nothing but, for any surface, is a normal vector to that surface. Okay, so we need to prove that. So let a surface is given by f x y z c. So this is a surface, means it can be just like any surface. Okay, this is your surface, and x y z equal to c. So this surface is given by this equation. Now on this surface, let's have this curve, means there are many curves can be find, means at any p point there will be infinite curves can be drawn. which is on this surface also and passing through P also. So this curve on this surface will satisfy this equation because this is lying on the plane on the surface itself. So that's why if curve C is given by this form Rs, Xs, Ys, Zs, so we already discussed this thing here, that we can define any curve in this form. This was your function for the curve. So if this is your curve, then these coordinates will satisfy this function also because this is for the surface. Now substitute Xs, Ys, Zs. So this will means this will also satisfy this equation for this. So this will equal to C. Now see, if this curve satisfy this equation, now at any point, or we can say this at this P point, we can find the tangent also, because as we did here, we have the surface and we find it the tangent. So here also we'll find this tangent. Now what will be the tangent? So F dash, let's find this. So R dash will be X dash, Y dash, Z dash. So this will be the tangent at point P for this curve. Now see, now let's check how F is changing with respect to S. So dF by ds will be nothing but, again we can see this thing is equal to this. So but according to this equation, this should be equal to 0 because it's for a surface. So this will satisfy this equation. So let's find the derivative of this equation with respect to S. So it will be df by dx, del f by del x, and dx by ds, then del f by del y, dy by ds, del f by del z, dz by ds, and this is constant, so this will give you 0 here. Now see, this equation can be written in this form, means this is nothing but x dash, y dash, z dash, and this is del operator. So we can see from here, this is nothing but gradient of f dot r dash, and this is equal to 0. So this 0 came out from here, from this equation. Now see, this r dash represent the tangent on this point P. Then this vector should be perpendicular to this tangent. Only then we can say this will be 0 because this is dot product, so it should be 90. So r dash represent the tangent, then this should represent a perpendicular vector to this tangent. So means this vector is perpendicular to P point also. Okay, so this surface, it will be perpendicular to the surface also on this P point and the tangent. So that's how you can say that this del f represents the perpendicular vector at this P point. So unit vector at this perpendicular P point will be vector del f divided by del f magnitude. So this will give you unit vector perpendicular to P at this surface. Okay, so that's how you determine. You don't need to remember this complete derivation. You must know that what gradient represent here. Let's see one example. Find a unit normal vector n cap on the surface at point this. So this is your surface. Now what is gradient? Gradient will give you perpendicular vector. So gradient of this will give you, means just take the derivative. It will give you 2x here, 2y here, and minus 2z, and multiply with 4 to all of them. So it will be 8x plus 8y minus 2z. Now this is your perpendicular vector. So at this point 102, substitute the value. 1 will be 8 and it will be minus 4. So this will be perpendicular vector on this point. Now if you need to find the unit vector, you can just divide it by its magnitude, that is 64 plus 16, that is give you 80. So under root 80 will give you unit vector in that direction. So this is perpendicular vector. Many questions frame from here. I have seen many previous year questions based on this. Now see, you can also find the what? If you can draw infinite curves on the surface at this passing through this P point. So see, at this P point, if you draw the tangents, then for every curve you will draw the tangents. So this tangent will make a surface, a plane surface. So they will make a plane here, these tangents. And if they ask you to find the equation of this plane, then how you can find? Now this plane is of tangents passing through the P and on these curves, infinite curves. So just like we can draw a tangent for any curve at any point, same for any surface we can draw a plane on any point. Okay, and that plane is made up of tangents at this point, at that point. Okay, so how to find the equation of that plane? Now see, equation of a tangent plane to any surface, let pxyz is given. So this is our point is given and its coordinates are x0, y0, z0. So this point P is given. We need to find the plane which is passing through this point. Let's say there is any other point q, x, y, z, variable point on the plane. So if you have any plane, so if this is your p point is given and you can assume any q point, that's how you find the equation of plane, means this q should satisfy this plane's equation. So these are the equation of q is the variables x, y, z. So what this pq line will be? Pq line will be q minus p. So q minus p, x minus x naught, y minus y naught, z minus z naught. So this will give you pq line. Now see, this line on means any line on this plane will always be perpendicular to this perpendicular vector. So the perpendicular vector at any plane is given by the gradient. We already seen that thing. So gradient multiply this pq will give you 0. So gradient of f at the p point dot pq should give you 0. So if you use this equation, this will give you the equation of that plane which is passing through the p point. So this is the equation of tangent, or the plane made up of tangents. Okay, so let's see an example of this also. Find the equation of the tangent plane to the surface. So we need to find the equation for the tangent plane to this surface, x cube plus x cube y square z equal to 12. So at the point this, we need to find the plane 1 minus 2 3. So there is any other point q, x, y, z for the plane. Let's see, find the equation. So pq will be given by x minus 1, y plus 2, 2 minus 3. This will be your pq line in the plane. Now perpendicular line to this plane will be gradient of this. So it will give you 3x square y square z, then 2y x cube z, then x cube y square z. So this will be your perpendicular. Now perpendicular at 1 minus 2 3, just substitute the value in place of x, y, z, 1 minus 2 and 3. You will get the perpendicular vector. Now this is perpendicular to your PQ line also. So PQ line we already get x minus 1, this one was your PQ line. So dot product of PQ with this perpendicular gradient f will give you 0. So we just multiply this and that one, so it will give you 0. Now after solving this, we will get the equation of plane, that is 9x minus 3y plus z equal to 18. So that's how you can find the equation of plane. Now see, you know what is del operator in the Cartesian coordinate, that is del by del x I cap, del by del y j cap, del by del z k cap. Now you must know the del operator in the spherical and cylindrical coordinates also, so you can directly use them. So if there is any function v, that is function of r theta phi, so gradient will be given by del r v, 1 upon r del by del theta v, 1 upon r sin theta del by del phi cap. So always remember this formula. And for the cylindrical coordinates, it will be del by del r cap plus 1 upon r del by del phi del upon del z cap. So this will be your del operators, or the gradient, how you can find the gradient in these coordinate systems. So let's see, we have given an example. This function is given minus k cos theta divided by r square. So this is in spherical coordinates. So you need to find the gradient of this. So we will use this one, this formula. So del by del r of this will give you 2k cos theta by r cube. Then 1 upon r del by del theta will give you cos theta minus sin theta. And it will be this 1 upon r del v by del theta will be this theta cap. And this is not function of phi. So del v by del phi will give you 0 and this will be 0. So that's how you will get your gradient of v will be this in the spherical polar coordinates. Okay. So always remember these formulas, very important. So that's it for today. Thank you everyone.